Hey everyone, how are you?
Good.
Good.
Good, how are you?
I'm good. I am good. I finally got the winds shifted since last week, and so I finally, in my my area anyway, I finally got some blue skies. And I finally got to go outside over the weekend, and I feel like a different person. It was helpful. Hopefully you guys have some clearer skies by you too.
Yeah, same here.
Good.
It was a lot nicer.
Alrighty. Let's see. Let me get all sorted here. Does anybody have any questions from the homework or anything really that we've talked about? Oh, sorry. Let me record. I always forget to record. Let me take care of that now.
This meeting is being recorded.
Okay, does anyone have any questions either from the last homework or any of the material we've talked about so far? Or any? Yeah, go ahead.
Yeah, number 12 on the homework.
12? All right, let me pull it up. So this last homework was a nice mix of lots more force diagrams. Hopefully you guys feel like experts at drawing force arrows now. And then some more ballistic motion problems, projectile motion problems. Now let's see. So, okay, I'm going to do a share. So problem 12, bullet shot from a rifle has a mass and is moving at a speed of that. And it strikes the target a distance of 47.7 centimeters as it comes to rest. Okie doke. What was the magnitude of the net force on the bullet as it penetrates the target? Now, I snuck this one in at the very end. We did some complicated F equals MA problems just to sort of show you what could happen, but we didn't do a lot of work with F equals MA. So I'm guessing a lot of people found this one tricky. Give me a thumbs up if you thought it was tricky, or you can say yeah. Or, yeah, okay. It was supposed to be tricky. It was my sneaky way of tricking you into doing stuff that we haven't covered. But I'll lay it out for you right now, and I promise the quiz isn't on this. All right. So alrighty. In the problem, they give you, let's see. First, I'm going to make my picture. I'm going to treat this the same way I treat every other problem. So I've got a bullet, and the bullet has a speed of 328 meters per second. And it strikes a target. So it crashes into something. And then it says it penetrates that thing 47.7 centimeters. So this is, like a mattress or something. And it goes in 47.7 centimeters. And when it says penetrates, it means that once it's here, the speed is 0. Okay. So we've penetrated an object 47.7 centimeters, right? So I had some speed. Over here, I don't have speed. So somehow in this region, I've got some acceleration going on, okay? And then I think that's it. I think that's, the other thing they give us the mass. So they say the mass is 12.8 grams. And I always convert to kilograms, meters, and seconds because newtons, for example, are in kilograms, meters per seconds. And if you use numbers that are grams, you'll end up with the wrong answer. So I'll convert this to 0.0128 kg. In case you're wondering how I did that, 1 gram is 0.001 kg. That's the same thing as saying 1,000th of a kilogram divided by 1,000. In fact, kilo means 1,000. So if I wanted to flip this around, I know I'm doing this to death. Hopefully you're not bored. 1 kilogram is 1,000 grams because kilo means 1,000. Okay. Enough stalling. So we probably, what the question asks is, what's the net force on the bullet? And I think that that's what is going to throw you off here. Because if I just said an object with an initial speed 328 comes to rest after moving 47.7 centimeters equals 0.477 meters, you'd be quite comfortable doing that, right? This is kinematics. And I could say V final squared equals V initial squared plus 2A delta X, right? Well, the final speed's 0, right? Because it comes to rest after it's done penetrating. And the initial speed was 328 squared, and then plus 2A times 0.477. So now I can find the acceleration. It's 328 squared divided by 2 times 0.477, and it's got a minus sign in front of it, and that indicates that it's slowing down. So I'm just grabbing my phone so I can get a number out of this, because we're going to take this number and we're going to use it. Anybody know what to do at this point? This is huge.
Would that be part of the force and mass and acceleration?
Exactly. Exactly. So I get some huge number here. This is like 112,771 meters per second squared. Okay. And so if I want to know the force, right, this tells me the acceleration. But in order to know the force, I have to know how big is the object that I made do that. And that's what this F equals ma guy tells you. It says, if you want to make something do this, I need to know how big it is, and then you know how hard to push on it, right? So I can just say times, let's see, 0.0128, 0.0128, that was the mass in kilograms, times negative 112,771. So that equals 1,443.47 newtons. Just point out a couple things. Number one, it's got a minus sign. Does anyone know what it means that the force is negative?
The velocity is decreasing?
Yeah, the velocity is decreasing. Another way to say that, though, is that it points to the left. You know, up here, I drew the thing pointing to the right, and I didn't put a plus sign here, but I didn't put a minus sign either. So really what I was saying is to the right means plus. And so if you ever find yourself wondering, what is a negative force, or what is a negative this? What does it mean for it to be negative? Minus signs only exist to tell you the direction of things. And so if you see a minus sign in front of something, your brain doesn't have to explode. It's not like, what's negative pressure? What's this? It just means it's pointed in the opposite direction. So that's all that minus sign means. Very good. And then the other thing I might point out, none of us have a really good, I think, intuition for newtons, because this is the United States and we use pounds for units of force in the United States. We're one of the only 2 countries in the world that still does. It's us and, gosh, I don't remember. Some very small country somewhere also uses pounds. India used to, but then they converted off of it. They're called British units, by the way, pounds, but the British don't use them because it's a terrible system. Metric is much better. The US tried to convert to the metric system, I want to say like maybe in the 70s, and then they were going to do it again in like the late 80s and early 90s. And we're stubborn. We don't want to change. Anyway, this is the last time we'll talk about pounds in this class, but 1 pound is about 5 newtons, right? So if you're wondering, like, what does this mean, 1,444 newtons? It's about 300 pounds, give or take. So what they're saying is that the stopping force for this bullet is 300 pounds, right? And then you can think about that and say, does that make sense? It kind of makes sense. I mean, if you were to get hit by a bullet, it's going to knock you off your feet. So if you got 3 pounds, you could probably say this can't be right. And if you got 3 million pounds, you would say that's crazy. That's enough to lift a building, and bullets don't lift buildings, right? So about 300 pounds is good. The only other thing, see, I never do numbers, but if we're going to do numbers, we should do them, right? The other thing that's interesting is we probably don't have a good notion of meters per second either. So if you want to know miles per hour, it's a little more than double the meters per second. So this is probably something like 750 miles per hour. Very approximate, right? But since we're talking about guns, you may get the trivia question. One day you'll be playing Trivial Pursuit and they'll say, which is faster, a bullet or the speed of sound? Does anyone know what the answer is? I see a chat. Hang on, let me see if I can find it. Shoot, I can't bring it up. Let me see if I can bring it up on this one.
I just said bullet.
Oh, the bullet. Yeah. Does anyone have a different answer? Oh, cool. Chat. Bullet. Okay. The correct answer is yes. Because there are subsonic guns and supersonic guns. Some guns are supersonic. They shoot bullets faster than the speed of sound. And other guns are subsonic. They shoot bullets slower than the speed of sound. And there's reasons why you might like one or the other, but supersonic bullets produce sonic booms. And those are very loud noises. And we'll talk more about that when we get to that unit. But yeah, I'm not going to. I'm going to stop talking. That's this problem. Okay, more questions. Okay, cool. So we'll do our quiz. Okay.
I think someone in the chat was asking for number 5.
Oh, that's what that, I saw a 5 and I was like, what does that have to, okay. Yes, thank you. Thank you. I'm starting to learn voices. That was Jose, right?
Yes.
Awesome. Yes. You know, faces are easier than voices. Much, much easier. Okay. Okay, so number 5. We'll bang this out. Okay, great. So let's go back to this. All right. So in number 5, oh, maybe I should let me do a share screen. Let me show everyone the problem in case you don't have the book handy. I'll do that really quickly, I promise. Okay, so this is drawing forces. It's someone pushing a box up an inclined ramp. Okay, so alrighty. So I'll draw the ramp. I'll draw the box, and then we're going to make a free body. So we draw a dot. Okay, and in the actual thing, the guy is pushing the box up the ramp with some force F. So that's the easiest one to do. I'll just put an F right here, and then that covers the guy, right? But I also know that the box is made out of stuff, and so the box has mass, and so the box has weight. We're going to talk about mass and weight today. So this mg stuff that I keep writing and I keep saying I know we haven't talked about, today we'll finally talk about it. And you'll say, oh, that's why he's been writing that the whole time. So the box has weight, and weight always points down. Okay. In addition, the box is sitting on a surface, and the surface applies a normal force. And remember, normal means perpendicular. So you don't want to draw, if I saw the normal force drawn like upward, I would take off credit because, look, we may not be great drawers and our arrow might be here or it might be over here, but it's definitely going to be at an angle. It is definitely not straight up. Okay. So the normal force points in this direction. And then they say that there is static friction, but oh, I see. I was like, it's moving. Okay. Kinetic friction. Okay. So it says you can use either FS or FK to denote kinetic friction. The problem says that the box is moving. So I write V up here. V definitely does not go on the free body diagram, right? Because it's not a force. I just put this here on my picture to indicate that the box is moving up the slope. And I know that friction will try to oppose this motion between the two surfaces. And so friction, ooh, funny F, sorry. Funny F, my force of friction points down the slope, okay? And then I put a K on it because they tell me that the block is moving, and kinetic friction is a little different than static friction. That, by the way, just as a refresher, we talked a lot on Wednesday about friction and like two surfaces having teeth and the teeth lining up with each other, right? When it's static, the teeth sink in really deeply. They're in there really good. So if you want to get it moving, it's hard. Once it starts moving, they just sort of bump along each other. And so kinetic friction tends to be weaker than static friction. Okay, but that's it. This is the free body diagram. We haven't done anything with it. We will, but that's it. That's the first step in every single force problem you do, is to make a free body.
Professor.
Yes.
Are there any cases where the kinetic friction is stronger?
Are there any cases in which kinetic friction is stronger than static friction? Gosh, I don't think so. But remember what we said, that this model we're using is like it's a pretty good model, and it covers it covers all the cases we're going to see in introductory physics. But that really, friction is the result of very complicated intermolecular forces, and I'm sure if I say kinetic friction is always stronger, some solid state, or kinetic friction is always weaker, some solid state physicist will come along and say, no, you're wrong, and here's why. But I can't think of a counterexample. So let's put it that way. I will say, for the purposes of this course, you're not going to encounter a kinetic friction that's stronger than a static friction. I'll also say, though, that there doesn't have to be a big difference between them. It really depends on the particular surfaces involved. So sometimes, like the static friction, I'll just make this up. Static friction might be 0.50, and kinetic friction might be 0.48. It really depends on the particulars of the surfaces, and evaluating this stuff from first principles, so from what are the molecules doing to make this force, is extremely complicated, and more sophisticated than the models that we need for this class. I'll say it like that. But it's a good question. I'm going to Google it while you guys take your test. All right. Let's stop this. Oh, number one. Okay, I'll do number one really quickly too. Okay. So this guy's pushing on a block of ice, and we're going to make a free body diagram. Okay. So this one we'll do a little faster. So this is problem one. Okay. And let's see, I had a block of ice and a person pushing on the block of ice in this direction. So this is F. Here's the ground. So I know that it's sitting on the ground, that there's a force in this direction, F. It has mass, so mass is pulling it down, mg. And I know that the surface is going to push it back up, with some force, normal force. Let me look at the problem again and just make sure that there isn't, let's see. It says that even though he's on ice, don't assume there's no friction. So in other words, say that there is friction. And he says he pushes it across the ice at constant velocity. So on my picture, I can write a V, but I want to keep my V as far away from my free body as I can because it doesn't belong on the free body. So I know that friction has to go in the opposite direction between these two surfaces. So this is friction kinetic. And it wouldn't hurt if I add theta. They don't give me a value for theta, so it's not super critical, but theta is shown in the problem that they give, and so I'll include theta in my free body as well. So if I were to solve this, my job would be to break things into components. It would be to break things into components, but that's we'll get to that when we get to that. For now, that's done. All right, cool. Okay. Oh, sorry. Yeah, I'll do number 7 too. Number 7. Let's do number 7. Okay. So number 7. Ooh, yeah, this is a good one to do. I think if anyone was rolling their eyes and going, oh my God, why are we going to do another? When you see the quiz, you're going to be really happy that Carlson has to do this one. So everyone pay attention. Okay. So this is the problem. It's a Jeep that moves 27 meters and then it breaks after a certain amount of time. So we'll make our picture. Okay. We'll make our picture. Okay. And expert TA. Okay. So here's my picture. It's a car. It's moving with a speed V, which is unknown. And it moves a distance D. It moves a distance D in 21.5 seconds. So this is T equals 0. This is T equals 21.5. And then it says after that, it breaks and it comes to rest in some other distance. D2, we'll call it. D2. And this time is T2 is another 7 seconds later. So I'm going to say delta T. I'll put deltas in front of these. 21.5. Delta T2 is 7 seconds. So this is just what the problem gives us. It says that this car goes 27 meters in 21.5 seconds, and it's accelerating, okay? And then it says then it brakes and it takes 7 seconds to stop, okay? And then they ask us for a whole bunch of stuff. So they say, what was the Jeep's average velocity during T1? So during this period, what was its average velocity, okay? So average velocity, V bar, that's just delta X over delta T. So that's 27 divided by 21.5, and that's some number, okay? Now notice it doesn't have to be going that speed. It just that's the average speed it's going, okay? But it's like we make this comparison all the time. You go to Dunkin' Donuts and you hit traffic lights and stuff. So, but on average, it takes you that long to get there. Okay. So the next part asks, what is the acceleration during the time interval T1, assuming the Jeep started from rest and moved with constant acceleration? Okay. So we have constant acceleration, and starting from rest means V initial equals 0. Okay. So I can say, so D equals V initial T plus 1/2 AT squared, right? V initial 0, because they said we start from rest. And so 1/2 AT squared, so that's 1/2 times A times T, which is 21.5 squared. All of that equals the distance, which they tell me in the problem, 27. And so A equals 2 times 27 divided by 21.5 squared. All right. That's the acceleration. And then the last part, they say, what was the Jeep's instantaneous velocity at the end? In other words, at this point here, what was its instantaneous velocity? And so now they're saying specifically, what was the Jeep doing here? I'm not interested in its average speed. I want to know exactly how fast it was moving when it was at that point. And so now I can say V final equal V initial plus AT. I found the acceleration from earlier, so I can plug that in here. The initial speed was 0, right? So I can say V final equals 0 plus that number, whatever number that is. I'll just say number, times 21.5. Okay, and then I multiply these two, that'll give me the final speed. And then at the end, they say, using the result from part C, what was the Jeep's horizontal acceleration during the braking? So now they're saying, okay, now that you know all that, what's going on here? What's going on here? Okay, so they give you delta T, and you know V final equals 0 because it's stopped, and V initial, that's this number we just calculated, right? It's V final for this first trip. We're calling it V final because it's at the end of this, but it's also a new beginning for the next leg. So it's also V initial. So we can come back and we can say part D, V final equal V initial plus AT. We can do it all over again. Only this time, this is 0 because it stops when it's done braking. And then V initial is this number up here. So number times 21.5 plus A, which is unknown. And then they tell us that this time takes 7 seconds. Times 7, right? So then that'll give you a little piece of algebra, and you'll solve that piece of algebra for A. Just some things, like just broad things to point out. Like without even calculating, we know that it takes 21 and a half seconds. It takes 21 seconds to accelerate from rest to this speed. And we know that it stops in 7 seconds. So the change in speed is the same for both legs. You go from 0 to V and then V to 0. Here you do it in 7 seconds instead of 21 seconds. So you know that the acceleration is going to be about 3 times as big as the other acceleration, roughly, because it's 21.5 instead of 21 and 7. Okay. All right, now for real, I am going to publish the quiz. 5 questions, 10 points, 20 minutes. I'm going to change the due date. Arg, I goofed you guys. Instead of making the time limit 20 minutes on the test, it's giving you like 3 days or something. So I'm just going to call time at 7:55. That also means if you finish early, you have till 7:55.
Professor? Excuse me, Professor.
You're on mute, Professor.
Thank you. Thank you. Yes, Max. I was just puzzling over whether or not I wanted to answer it, but I want everyone to hear it. So go ahead and ask your question.
What does it mean, like relative to the Earth in question 5?
Great. So question 5 says, true or false, friction always slows an object down relative to the Earth. So what I mean is, if you're standing still and you're standing on the Earth, is it true that every single object that you observe in all situations will always slow down relative to you because of friction? Will friction always bring things to rest relative to you standing on the ground? Okay, everyone's done. Let's just curious. I'm gonna see. Let's see. Quiz statistics. I'm gonna see what most people missed. Most people got the first one. That's good. Most people got the second one, about 50%. Less than 50% got the third one. More than 50% got the third one. And then the last one, 64% got correct and 36% got incorrect. I think once I started talking about it, people had an idea that something funny was going on. So let me, that's why I didn't know if I wanted to answer Max's question. But let's do this. If you remember, oh, here, I'll do it here. If you remember last class, we looked at this video. So if I push the top one moves and the bottom one doesn't, right? But if I push the bottom one, so just to be clear, I'm not pushing on the top one. They're two totally separate objects, right? The only force acting on the pink one is friction. And so even though I push on the bottom one, friction speeds it up. Friction actually accelerates it. And the point I wanted to make with this is that friction cares about the relative speed between two surfaces. It doesn't care ultimately about what the speed of something is relative to the Earth. So that's why Max asked, he said, what do you mean relative to the Earth? Well, I'm on the Earth right now and I'm stationary relative to the Earth. But when I push on the bottom one, neither one of them is slowing down relative to me. They're both speeding up, even though friction is the only thing acting on the top one. Let's look really quickly at the other ones. I'll just do it. Share screen. Ooh, we don't want that. This is where we, well, this is good. Okay. So, let's see. Let me find it. Let me just make sure that I'm saying the right stuff. It says a Jeep starts from rest. So it starts from rest and it travels a distance of 32 meters in the positive X direction. And I say it takes T equals 4 seconds. And then they say, what is the average speed of the Jeep? So V bar, that's delta X over delta T equals 32 over 4, 8 meters per second. Okay, that's A. B said, what is the acceleration of the Jeep? So here we can say X final equal V initial T plus 1/2 AT squared. So this starts from rest, 0, plus 1/2 times A, which is unknown, times 16. Okay, so this says 32 equals 8 times A. So A equals 4. Okay, and then the next thing asks, what's the speed of the Jeep at T equals 4 seconds? So V final equals V initial plus AT. So that's 0 plus 4 times T, which is 4, or 16 meters per second. So notice it's actually at the end, it's actually going twice as fast as its average speed. But that makes sense because at the beginning, it's going much slower than its average speed. And then somewhere around the middle, it hits its average speed and then it goes faster. So the slowness it has here is made up for by the quickness it has on the second part because it's moving much faster on the second part. Okay, let's analyze D, question 4, right? Which was, here's a box, and let's see, we've got T2 up this way, T1 this way. This was inspired by the bowling ball problem on your homework, but the idea is this, right? T2 has to, is the only force that's vertical, that has a vertical component to it, right? So T2 has to balance T3, right? If we want to get fancy, you don't even have to go this far, but if you want to get fancy, if you start labeling the angles, here, let's label this angle theta, you can actually say that T2 sine theta has to equal T3, and likewise, T2 cos theta, T2 cos theta has to equal T1, okay? So for sure, T2 is the biggest. It absolutely has to be the biggest. And you don't even have to get too much into this trig stuff to see that. You can just say that T3 points up and to the left. It has to cancel all the stuff that's to the right, and it has to cancel all the stuff that's down. Therefore, it has to be bigger than both of them because it kills both of them together. And then there's the question of, okay, well, which is bigger, this one or this one? And then the answer there is, well, look, T2 in the diagram was much more vertical than it was horizontal, which means the bulk of the work that this arrow is doing is in the up-down direction. So the biggest part of this, sorry, let me draw this clearer. Just in terms of pictures, this is T2. T2 is made up of two vectors. It's made up of these two little parts, T2y and T2x, right? Well, it's clear that if you're at a very steep angle, this vector is bigger than this vector, right? So if you like trig, you can do it with trig. You can say, well, for steep angles, sine theta is bigger than cosine theta. So therefore, T3 must be bigger than T1. Or you don't even need to go that far. You can just take a look at it and say, well, I know that pictorially vectors are made up of arrows, and for the steeper, the horizontal arrow is going to be much smaller than the vertical arrow. So therefore, the vertical thing must be larger, okay? And then for question 5, oh, I already answered question 5. That was our video. Okay, does anyone have any questions about that? Okay, cool. Sorry, let me just make sure. Okay, great. So we do have a lab today. Originally, I was going to do the lab before the break, but because we only have about 20 minutes before the break, I'm going to switch up the order a little bit. So we're going to talk about mass and weight, and we'll look at a couple example problems. And then after the break, we'll go back and we'll do the lab. It's listed under assignments as lab 7. And I'm going to modify it from what it is in the module, because the videos that go along with it actually forgot to tell us something very important. But that made me very happy that it forgot to tell us something very important, because it gives us a whole new way to interpret the same procedure. And we're actually going to solve, they were supposed to tell us the weight of these little masses they use, but the video doesn't have that information in it. So we're going to use their procedure, and we're going to use their data to figure out what the mysterious weight is supposed to be. So the module, the questions that could ask will be a little bit modified, but it'll be a fun lab because we're solving a mystery, a real life mystery, not one that I invented. We literally, I don't know how to do lab in the module because they didn't give us this information. Okay. So we are going to talk about, finally, we're going to talk about why I keep saying that weight is equal to mg, right? The idea is this: we know that F equals ma, right? And the other thing we know, I think we've talked about this, but if we haven't, we're going to talk about it right now. If you can do this experiment, right? If you take a penny and a quarter and you hold them at the same height and you drop them, they're going to hit the ground at about the same time. Now, it may be a little bit different, right? But that's very interesting because a quarter is a lot heavier than a penny, right? Our notion is that light things fall slowly and heavy things fall quickly, but that is completely wrong. It is completely wrong. A mattress, which weighs 100 pounds, will fall slower if dropped from a high ceiling than a 10-gram steel ball, right? And the reason for that is because the mattress gets a lot of air resistance. It bonks into a lot of air molecules. I don't know if you remember last time we talked about doing a belly flop. We talked about doing a belly flop when you hit the water and why that hurt so much more than going in feet first. Well, the same thing happens when you move through the air. And if you're a big fat mattress, you bump into a lot of air molecules and they slow you down. If you're a sleek steel ball, you hit very few air molecules. So the reason why we seem to think in our brains that light things fall slow and heavy things fall fast is because we're thinking about things that have different dimensions. We think of large objects as having a lot of expanse to them, and that really contributes to air resistance. But the truth of the matter is, if you got rid of air resistance, everything falls to the ground at the exact same rate. Everything. If you go to the moon where there's no air and you take a hammer and a feather and you drop them at the same time, they hit the ground at the exact same time. So if you're thinking, well, that's ridiculous, no one would go to the moon and do that, they did it. They literally took a hammer and a feather, the Apollo astronauts, they literally took a hammer and a feather and dropped them at the same time. And I encourage you to YouTube it. The only reason I'm not showing you the video is because it's crummy quality. It's hard to tell what's going on. So, but YouTube it. Apollo astronauts, hammer and feather. They took the time to do this on the moon. They fall at the exact same rate. Okay. So all of that is to say that if we're not considering air resistance, if we can somehow make the objects similarly shaped, right? It doesn't matter how heavy they are. It doesn't matter how massive they are. They all fall. Their acceleration is all g equals 9.81 meters per second squared. This number actually varies a little bit depending on where you are on the Earth, but it doesn't vary a lot. So normally you'll just see 9.8 quoted as g. We've been using it for free fall, right? Like all those free fall things we did, I never told you how much anything weighed because I didn't need to. I'll say one more thing about that in a second. But so if I want to accelerate something with an acceleration g, then I know from Newton's law that I have to put on a force of it, which is m times g. So apparently the force that the Earth pulls us with is mg, but that's exactly what we mean when we say weight, okay? So that's why in all these force diagrams, I keep writing mg as the weight. It is, okay? Now the thing about this is that it's super unsatisfying. You have absolutely no idea why this happens. I've just said, oh, look, everything falls at the same rate. Therefore, this is the force that the Earth exerts on us. And you could say yes, and it's a very nice kind of experimental explanation of what's going on. But all I'm really doing is telling you what you can see. I'm not explaining how any of it works, right? And so Newton, one of the reasons why Newton has a unit named after him is because Newton figured out how gravity works. At least he did a first pass at it that's really good. Einstein had to fix it up a little bit. But Newton wanted to know not just why things fell at 9.8 meters per second. Newton was looking at things like the moon orbiting the Earth. And Newton really wanted to know, why does the moon orbit the Earth, right? He understood that the moon was tracing out a trajectory and that the moon had to accelerate. It had to be accelerating, and it had to be accelerating toward the Earth. And he knew that since it had to be accelerating toward the Earth, that there must be some force on the moon. And you might say, well, what's making that force? Well, it's being pulled toward the Earth. Maybe the Earth is making that force. So Newton was obsessed with the idea that the Earth was pulling on the moon, and in turn, the sun was pulling on the Earth, and the moon, and that somehow the same force, there's the story of the apple falling on his head from the tree, right? The apple falls on his head, and he says, oh, well, the same force that makes the apple fall on my head makes the moon fall toward the earth, right? So Newton thought of this problem not as one object moving in a circle around another. Newton said, no, the moon is falling toward the earth all the time. It's just that it's moving so fast that every time it falls a little bit, it hasn't gotten any closer. So the moon is perpetually falling toward the earth, and it's never getting any closer because it has this magic speed such that the amount it falls by just causes it to change its angle a little bit. So to put that another way, look, the moon is lower here. The moon is lower here. It has fallen, but the earth is lower here too. So the distance between them hasn't changed, right? Somehow that works itself out magically. And he played around a lot with a lot of ratios and stuff. I don't know if this story with the apple is true. It's probably not. But Newton had a lot of time on his hands because, we are experiencing COVID plague right now. It's a plague. In Newton's time, in the 1600s, bubonic plague was going around, Black Death. And in London, it killed something like a quarter of the population. Crazy sickness. And Newton was in college at the time, and he got sent home. They sent everyone home because it was bad news, this plague. And it was during the time that he was quarantined that he had some of his biggest discoveries. It's said that he thought of his theory of gravity during quarantine. It's said that he invented calculus. Newton invented calculus. Leibniz would disagree with him. I don't know if you guys have ever taken calculus. You see there's like this big dispute about who invented it, Newton or this other guy, Leibniz. And the truth is they both invented it, and they were both interested in very different things. They invented equivalent systems. Leibniz's notation is the notation we use today. Newton's calculus is crazy. It's very hard to follow, but it is the same thing. It is the same thing. Okay, anyway, Newton played around and he played around and he played around and he came up with this. This was his idea. And when we start doing circular motion, I will show you how you can predict the motion of the moon using this equation. This equation works really, 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 really well. It is not perfect. And there's some things that you can't predict in the solar system based on it. It's not that the calculation's too hard. It just doesn't predict this behavior. And so that's a limitation of the theory. But people always assumed that it was because we weren't good enough at calculating. This looks, well, anyway. But Einstein actually modified the theory and predicted this. Mercury does this really funny thing. Here's the sun. This is a bit of an aside, but Mercury does this really funny thing where when it's at the end of its ellipse, it doesn't continue in the same ellipse again. It actually starts a new ellipse. And then it starts a new ellipse. This is called the precession. None of the other planets do this, but Mercury does. And it's super bizarre. And you literally cannot explain it using this law. And so Newton is such a giant among physicists that it was considered sacrilegious to say that this was wrong. But Einstein actually had another idea, and people were dismissive of it, and they said he was crazy. But Einstein actually predicted, with his model, he was able to predict the precession of Mercury, right? And so that's the first good test of a model. It explains behavior that you've already observed, right? The next test of whether a model is good or not is, can it predict new behavior that you haven't observed yet? And Einstein's theory of gravitation predicted new behavior, bending of starlight that no one had ever seen before. And he didn't have to wait long. It was only 4 years after he invented general relativity, it's called, general relativity, that people were actually able to observe the bending of starlight. And this thing, which was basically religion, people did not question it. It crumbled. It crumbled immediately, and people had to accept general relativity. So I was going to make a big nutshell video about general relativity, but I was just fooling around on YouTube, and I saw there was already a great video out there. So I included that in the nutshell videos. There's a really great video that explains and goes into a lot more detail on some of this stuff I'm talking about. Anyway, all of that is to say, this is an extremely useful model. it's very useful unless you're going to look at some really weird things. And for all the stuff we're going to calculate, we would be crazy to use general relativity because general relativity is so much harder to use. And you don't get much bang for your buck unless you're looking at these weird esoteric things. So we're going to use this model. And what this model says is if you have two objects, this has a mass m1 and this has a mass m2, and they're separated by a distance r, okay? Then each one tugs on the other one. So the force that one exerts on two, so one pulls this guy to the left, that's equal to G, which is called Newton's gravitational constant. It's right here. It's a number that you'll pluck when you need it. And this is experimentally determined, 6.67 times 10 to the minus 11. I could tell you it's some of the most genius ways that people have of measuring these things. Yeah, but I won't because otherwise I'll talk about it forever. We'll just move on. We'll just say that some very clever people found some very clever ways to measure these things to great precision. So that number times whatever the first mass is, times whatever the second mass is, divided by the distance between them squared. So notice that the farther away things get, the force diminishes very quickly, very quickly. Just to give some numbers, right? If M1 was 1 kilogram and M2 was 2 kilograms, right? Then M1 would pull M2 to the left. So the force that 1 exerts on 2, I'll put a minus sign in front of it because it points to the left. So G, that's that number, times 1 times 2. And if I put them, let's just say R equals 2 meters apart, 2 squared. So this looks like G times 2 divided by 4 with a minus sign. And remember, the minus sign just says it points to the left. So this looks like minus that number G divided by 2. And that's newtons, right? Meanwhile, just like M1 is pulling M2 to the left, M2 pulls M1 to the left, to the right, exactly the same hardness. So it's pulling M1 to the right, G times 2 times 1 divided by 2 squared. So this is plus G over 2. In other words, every object pulls on other objects exactly as hard as they are pulled by that same object. You might at this point say, well, wait a minute. If the forces are the same, shouldn't everything move the same way because they all have the same forces on them? And the answer is no, because this is only half the picture. Once you know the force, you find the acceleration or the motion of the object by looking at that thing's mass. Things have different masses, and so gravity moves them in different ways, even though the force on the objects is the same. Okay, one thing really quickly. I just want to show you what happens when the distance gets bigger. So let's say same scenario as before, but now instead of R equals 2 meters, let's make it R equals 4 meters. So they're going to be twice as far away, 2 times as far. And let's calculate the new force. F12 equals G times 1 times 2, but now divided by 4 squared. So that's 2G over 16 or G over 8. In other words, I doubled the distance and the force became 1/4 as much as the original force was. So this is a force that gets very weak as you move away from it. Okay. It turns out to be the dominant force in the universe only because there's so much mass in the universe. There's mass everywhere, and all mass attracts other mass. There's no repulsive gravitational force in Newton's model anyway. Whereas if you remember from your science classes in high school, like charges repel, opposite charges attract. So that says that electric forces sometimes pull things together and sometimes push them apart. If you look on big scales, those forces tend to cancel out. Whereas gravity always is attractive. So even though it's very weak, all the forces always add together. They never cancel each other out. And so that's why gravity is responsible for why the Milky Way moves the way it does and why the Earth moves around the sun. Electric and magnetic forces have very little to do with it. Okay. Did I want to say anything else about that? Your book makes a good point. The mass of the Earth, just to put things in perspective, if you're not good at converting kilograms, so kilograms is a unit of mass, not of weight. People will often use the words mass and weight interchangeably, but mass is your inertia. It's your resistance to an acceleration, okay? Weight is how hard the Earth happens to pull on you, right? In other words, if I move you to another planet, you will have the same inertia. You will have the same resistance to acceleration, but that planet will pull on you in a totally different way. And so your weight will be totally different. Oftentimes people will say, how much do you weigh? And someone might say 50 kilograms. That's actually incorrect. They have a mass of 50 kilograms. If anyone ever says they weigh a certain number of kilograms, it's actually incorrect. So that's one sense in which the British units, pounds, are good, because if we say we weigh 175 pounds, that's a true statement, right? By the way, I looked it up while you guys were taking the quiz, and there are 3 countries which use imperial units: the United States, Myanmar, and Liberia. Everywhere else in the world uses the metric system. Even Britain, which invented the system, has abandoned it because it's very hard. Just think about like feet and inches. There are 12 inches in a foot and 3 feet in a yard and 5,280 feet in a mile. I mean, that's bananas. Converting all that stuff's a real pain in the butt. Kilograms, 1,000 grams. Kilometer, 1,000 meters, right? It's much, much easier to work with those units. And that's why G is given in meters per second squared, not feet per second squared. Although, since we live in the US, I'll just tell you, G is 32 feet per second squared. So 9.8 meters per second squared, or 32 feet. Whoops. Let me do that. Are there any questions so far?
No.
Okay, cool. I'll keep going. They could be bananas questions. You're like, if you've heard about something in the world and it's not like super specific, but you're like, hey, is it true that this is? But if it's related to gravity, yeah. So it is. I will just say, just something to puzzle over, right? Newton's model is extremely, extremely successful. But here's a question for you: how does it work? How are they pulling on each other? It's magic. I mean, it's a mathematical model that happens to work, but it's completely unphysical. What's the mechanism? How do they touch each other, right? What is pulling? It's very strange. It's very strange. And not only that, somehow, if I change the mass over here, magically, no matter how far away I go, magically, the mass over here will feel it. That's also very strange. How are they communicating with each other? They're not sending light signals to each other or anything like that. So how do they know? And Einstein tackled that problem too. If you've ever seen, well, I'll let you watch the video. If you're interested in that, watch the video. And if you're interested more, shoot me an email. I'll give you all sorts of resources. Let's 822. Let's just go over some of these questions together really quickly. Then we'll take a break. Then we'll come back and do the lab. So they want to know, so what's the standard SI, international unit for mass? Kilogram, always kilogram, okay? Now, I'll just throw this open to you guys. What's the mass of a 5 kilogram rock on the Earth?
5 kilograms.
Okay, Graham.
Yeah. What's the mass of a 5 kilogram rock on the moon?
5 kilograms.
5 kilograms. Easy, right? What's the standard international unit for weight? Anybody know?
Pounds?
You'd think pounds are a unit of force, but that's the imperial unit. What do we think the metric or SI unit? Newtons. Carlson says newtons. Absolutely. Weight is a force. Therefore, it's measured in newtons. And you don't need a special unit for something that is, after all, just one of a zillion forces we can talk about. Okay, so it's newtons. How about what's the weight? Now we're talking weight. What's the weight of a 5 kilogram rock on Earth? Anybody know?
About 15 newtons.
Beautiful. I love that you said about 50 because it's 5G. So 5 times 9.8 or about 5 times 10. So 50 newtons. In other words, we multiply by the acceleration due to gravity. Okay. And that gives us the weight. On the moon, it's 5 times whatever the heck G on the moon is. We'll learn how to calculate that, by the way. Whatever the heck a G on the moon is. I think G on the moon's like 2 and change. I'll Google it during the break. Let's just say it's 2. It's about 2. So 5 times 2 or 10 newtons. Okay. And then they just keep asking the same question over and over and over. When we come back, I'm not going to answer these. When we come back, I'm going to calculate, or after we do the lab, I'll calculate G on the moon and I'll calculate G on the Earth. I'll use Newton's law to show you that this is 9.8, and I'll use Newton's law to show you that this is some other number, 2.3 maybe. I don't know. I'll look it up at the break. Let's take our 20 now. So it's 8:25. We'll come back at 8:45. I'll wait one more minute and then get to work. All righty. So I just thought I'd show really quickly, I promise it is fast, where this 9.8 number comes from, if you know Newton's laws. Newton's universal law of gravitation is what it's called, by the way. So if I want to know what is the acceleration of an object on the surface of the Earth, okay, then I say that the Earth and the object attract each other. And this is a bit tricky because what's the separation between these two things? On the one hand, you might say, oh, well, the separation is zero because it's on the Earth. But on the other hand, the Earth is an awfully big place. And maybe you're separated only a little bit from this piece of the Earth, but this piece of the Earth, you're very far from, right? So you're being attracted to each piece of the Earth, and some of the Earth is very far away and some is very close. But we'll examine something later called center of mass. But for the time being, you can just think of this as, okay, the average location of where all that mass is at the center of the Earth, okay? And so I can view all of the mass as being located at the center. And that means that the distance between those two is actually the radius of the Earth. So you can say that the force on an object is this guy G times the mass of the Earth times the mass of whatever our object is divided by the radius of the Earth squared. And that, if that's the only force acting on it, that's equal to the mass of the object times the acceleration. Notice I'm interested in finding the acceleration of my object, not the acceleration of the Earth. And so that's why I say this force equals the mass of the object times acceleration, okay? In that case, I can kill these because there's one on each side. And then I can plug in all these numbers. So for G, I should write G again. G is 6.67 times 10 to the minus 11. And to keep myself honest, I will actually do it on a calculator and not just write 9.8. So 6.67 times 6.02 divided by 36. And then minus 11, 12, 23, 24. But I get this. I don't know why I get it, but here, now you know I'm being honest. I get 11.1 meters per second squared. I goofed up one of the numbers. I'm not sure how. Let's see, the mass of the Earth is up here. Oh, I know what I did. It's 6.4, and I put in 6. Okay, I know what I did wrong. Let me do this one more time. Okay, great. Now, when I put in the numbers correctly, I get 9.803 meters per second squared. Okay, I'm going to do the exact same calculation, but now I'm going to do it for the moon. The moon is the same as the Earth. It's made of stuff, and that stuff is located at the center. I just use different values now. So instead of mass of the Earth, I use mass of the moon. Notice the moon is a about a 30th the mass of the Earth, 1/30th the mass of the Earth, and its radius. Moon radius. Just look this up. Sorry, stand by. Everything I just said, getting done about how no one should use miles, no one should use miles. But of course, like the NASA website has it listed at 1,079 miles, right? So that's the radius. But let's put it in kilometers, which is more sensible. NASA, of course, is a U.S. government organization. 1,737. So 1,737 kilometers. So that's 1.7 million meters. Okay, stand by. I'm just going to do this really quickly. 6.67 times 1.6 divided 1. Okay, I get about 3.7. Let's see. I don't know. That doesn't sound right. That sounds way too big. But we'll see. Let's see. Acceleration due to gravity on the moon. They say 1.625 meters per second squared. That is not good. 6.67 times 10 to the minus 11 times 1.6 times 10 to the 23 divided by r squared. So 1.7 times 10 to the 6. Just show you what I'm doing. I did this and I got this. I will fiddle with this and find out what I did wrong while you guys work on the lab. That way you don't have to watch me fumble it. Okay, but the key takeaway I wanted to show you guys from this is this idea of thinking of all the mass as being at the center of a planet, and then the distance between two things. The thing that is at the surface of the planet is the planet's radius away. It's the planet's radius away. Okay. Any questions other than why did I blow it? I'll fix it, I promise. All right. Okay. So we're going to do this. We're going to do this lab. And then after the lab, we'll do some practice problems with Newton's laws, and then that'll set you up for the homework. So originally in the lab, if you watch the video, you see basically what they do is there's a cart, and the cart is pulled by a hanging mass, and that causes a certain acceleration of the cart. And what they do is they keep making the cart heavier each time, and the acceleration changes each time. And the goal is to show that force and acceleration have a linear relationship to one another. That F equals ma thing that we keep talking about. All right, that F equals ma. That's the goal. So it's a linear relationship, right? The slope should look something like this. The problem is when they ask you to take data, they say, oh, well, we've added 2 bars, these hexagonal bars. They ask for, yours module is a little different than this. They say, what's the total mass of the cart when it's empty and when we've added 2 of the masses or 4 of the masses? The problem is we don't know what those masses are because it's not in the video. If we were in the lab, we'd weigh them, but we can't. So instead of abandoning this, I decided that what we'll do is we'll use F equals ma. We'll say F equals ma is true, and we will look at the acceleration and look at the force and solve for the mass. Now, we know what the mass is empty. We know what it is. We can solve based on the force and acceleration. We can find out what the total mass is when it has 1 of the hex bars in it, 3 of the hex bars and 4 of the hex bars. And then what we'll do is we subtract out in order to find what the mass of each hex bar is. Okay. And then what we'll do is we'll take a little average. We'll find the average of these, and then that'll be what the hex bars are. I think they're around 100, but they may not be exactly 100. And then at the bottom of the lab, I added this one question. So what is the average value of the mass of the hex bars? Of hex bars. Okay. Let me do a quick share. I'll just bring you to the page really quickly. Okay, so assignments, lab 7. So hopefully you've had the opportunity to watch the video. The first video, he's just calibrating. Okay, he's just calibrating. The second video, he shows his procedure. The the one with 2 masses, something goes awry in that video. And you'll see in the video, he's like, oh, the force changed, but that shouldn't happen because he's always hanging the same amount of weight on the trolley. And that weight is what determines the force. And so he actually suggests that we discard the second data set. And I put it up here anyway. So these are screen grabs. I put it up here anyway, just so you could see it, but we'll ignore this, the 2 mass one. And we'll just do 1, 3, and 4. He also says that this is the cart with nothing in it, but it is actually the cart already. It has 1 hex in it. The mass of the empty cart is written behind him on the board. He says it's 392 grams, and I will take his word for it. This is with 1 hex bar on it. This is with 2, but we're going to throw that away. This is with 3, and this is with 4. So if we can find how much total mass we're moving each time, we should be able to figure out how much of that is attributable to those hex bars. Okay? And then our goal for this experiment will be find the mass of the hex bars. Does anybody have any questions? Okay, and of course I'll be hopping around to help. So I'm going to put you into breakout rooms. We'll spend, I don't know, 30-ish minutes on this, and then we'll spend the last 30 minutes solving problems. Oh, wrong one. Okay. 22 participants. 6. So there'll be either 3 or 4 people in each room. Is that right? Yeah, that's right.
Hello, did you guys watch the videos?
Not yet. Right now I have a cart that has a mass of approximately 392 grams. We're going to be measuring its mass and acceleration and force through the force sensor and the accelerometer. Xavier, you ready to collect some data?
Yep.
All right, tell me when.
3, 2, 1, go.
Okay, so you can see the force appears to be fairly constant. The acceleration is also fairly constant. Right now, Xavier is going to grab the force data and figure out the median value of that range of constant force values.
Oh, nope, not that way.
There's even one on the, you can click on the statistics button on the toolbar. All right, and yeah, he's going to mouse over it. There we go, that'll work. And you can see that the mean value is 0.408 for the force. For the acceleration, the mean value is 0.872. So those will be the first pieces of data you need for analyzing this experiment. At this point, we're now going to go ahead and collect the rest of the data. We have a set of hexagonal masses that we're going to be inserting into the cart. And Giovanni, can I get those hexagonal masses off cart and repeat this experiment? All right, Xavier, you ready?
Yep, 3, 2, 1, go.
Okay, and we're going to go ahead. We've changed the mass of the cart slightly. You can tell right away he's going to leave that up. Go ahead and drag that so we can see it. There we go. All right, our mean force
Yes,
did
just
not
let
change.
us know when you
It's
get your
0.408. Our mean acceleration is
Like, just let us know when you guys are done watching the videos.
now 0.872. Okay, and we're going to go ahead and add a second mass to the cart. All right, Xavier, let me know when you're ready.
3, 2, 1, go.
Okay, now we can see that our force did change somewhat this time, and so did our acceleration. So if we take a look at the mean value in this region, let's see, I think we're going to have to go ahead and grab that again. And guess we want to analyze the latest. All right, so now our mean force is 0.296, and our mean acceleration for the latest run is 0.408. So we definitely saw a change in the acceleration and the force. Now I think we're going to go ahead and add our third mass. Run this again. All right. Somebody let me know when you're ready.
3, 2, 1, go.
Okay.
I'm gonna All right.
And our force is 0.429. All right, we're going to do our last trial. And in our last trial here, let me know when you're ready, Xavier.
3, 2, 1.
Okay. And we're going to see that our force did not change appreciably. Our force is a value of 0.433. Our acceleration, on the other hand, has changed, decreasing to a value of 0.459. So we've done 5 different trials, each time adding a mass. Now I'm going to suggest that the first trial we did with no mass was accurate. We had some experimental problems in the second trial, so I'm going to suggest you ignore that with just 1 mass, and just consider our last 3 with 2, 3, and 4 masses. Something interesting happened in the second trial where the value of force went down slightly. I'm going to encourage you guys to look at the experiment and see if you can figure out what happened that time. Also, there's a series of questions for you to answer in this experiment. Good luck!
If you guys need anything, just give me a holler. I'm going to be floating around.
Thank you.
Oh no. Shoot. Sorry. How do I undo that? I'm sorry, I don't think I can undo that. Nuts. Okay. So let me broadcast to everyone. I'm going to have to make new rooms. Sorry, that was foolish of me.
Is everybody done already or not yet?
Actually, I think you're going to be in the
This
same rooms you were in
meeting is
before.
being recorded.
Okay, I just need to stay away from that button.
Okay, got it.
Okay.
Is everybody done with? Is everybody good now?
Yes.
Yeah.
Yeah. And then that's
The three.
that's
Oh,
written.
sorry. Is it the 392? That's the unloaded cart.
Yeah, that's what I put.
Oh yeah.
I got 0.392.
So the average acceleration for the first one is at the for the first trial is at the 0.872. Yeah,
It should be the 0.872.
yeah.
So far, so good.
Yes.
Awesome.
And then the next one is the second trial, which is still it's the same 8.872. Oh no, hold on. 4, no. Oh wait, sorry. It's 0.408. It's the one that's
Yeah.
says run one. Yeah.
Yeah. Don't forget to put units in your answer.
Or number. With a so the force for each trial, right? Yeah. So with the empty one, the 4, if the acceleration is 0 and the force was also 0. Total mass required slope. Acceleration? Oh, for the empty cart though. Oh wait, hold on. So initially, oh yeah, you're right.
For the 0.4, number 7, isn't that from number 2? Because I remember he said to ignore the second one and only just do 1, 3, and 4.
0.408. Yeah, that's the first trial. And
Oh.
that's the force. Yeah. And then the second graph in blue, that's the acceleration, which was 0.872. Yeah. I know it's just like going back and forth. So then it should be so the slope for the first one, the first trial was 0.46 or 0.47, right? 0.47. Since the force is 0.408 divided by the acceleration, which is 0.872. Did I do that wrong? Yeah. The acceleration, yeah. I got 0.46.
Oh, hey, make sure you modify the table. The way so if you're looking at the assignment, if you hit refresh, I show how to modify it because what you'll want to do is a little different, a little different. So if you're on the assignment page, if you refresh it, there should be a yeah, yeah. And so the first data point you're taking, actually, there's already that first data table. It already has one of the hexagonal weights in it. But you will need to know that that 392 number will be useful. Cool.
Okay, so number of masses is 1. So on the first trial, there wasn't any mass, right? Okay. Yeah. Oh yeah, that there was a mass on that one. One, two. One, four. Hold up. So it was for the one mass, and it was. I got 0.40. Oh wait. Yeah, 0.47. Oh no. Oh wait. Was that current for? Oh yeah. 0.47. Sorry. It's just that I'll keep going back and forth. I'm sorry. Number. I would like the little, yeah. So extra mass is equal to total mass mass the of the empty cart. He sent a message. Yeah. Yeah. He sent it like not on the, you know how he sends like those like pop-up messages into the group, not the chat though. I have no idea. I just saw it and I took a screenshot. He just put extra mass is equal to total mass minus mass of the empty cart. It's the mass of the load. Oh, another one. Oh, I couldn't take a picture in time. Yeah, that helps. Or I'll just have him come in the room. Can you see our chat? Oh no, I think it's just in our group.
Alrighty. No, I should. Well, when I enter the room, I get to see the. Oh, wait a minute. No, I see the chat from different rooms. That's interesting.
Oh, we saw that you. Yeah, sorry. We saw that you sent a message, but we couldn't read it all the time.
Oh, okay. So those are broadcast messages. So there's chat and then there's broadcast. So when I chat in a room, the chat goes only in the room. But when I send broadcast, it goes to all rooms. So the broadcast message said, there are 3 graphs, and the 3. Let's see, the 3. Sorry, there are 4. I'm sorry. The broadcast message said there are 4 graphs on the assignment page. The first one has 1 mass. The second one has 2 masses. The third one has 3, and the fourth one has 4. You don't want to use Oh, that's yours. I was like, what is my computer doing now? The second one is for two masses, and don't use it. I put it there just to show you how things can go haywire in experiments sometimes. I don't know why the professor doesn't, who's showing the experiment, doesn't know why it did either. He's like, I don't know what happened there, but you can talk about it. The force should always be the same, but in that one, you'll see it dips down, and it's, I don't know why the cable got twanged or something. Who knows? So that's all that said. That's all that said.
Okay.
Yeah. So like I'm checking this out here, Gilbert, and it's so the number of masses, you've got one mass, right? Your slope, that's F over A, is 0.47. So that's 0.47 kilograms, which is the same thing as 470 grams, right? So the total mass being moved is 470. The empty cart is 392. So how much must be attributable to just that hex bar? You understand what I'm saying? Okay. Okay. So let's replace the 0.47 is correct. Can you write after that equals 470? Grams. Great. Okay. So your slope, the mass of the thing you're moving, is 470 grams. But the empty cart without any hex things in it is 392 grams, right? So the total mass you have now minus 392 will tell you the mass of the hex bar. 78. So you've got, 78 grams, and that's the total load. So the extra mass is 78, and the mass of each hex is also 78 because there's only one hex. Does that make sense? In the other ones, maybe when you do 3, you'll expect to see the extra mass be about 3 times that. It won't be perfect because it's an experiment. And then you'll find the mass of each hex by dividing that by 3. Cool. Leave it in grams only because yeah, leave it in grams. If we were going to do something with that number, if we were going to calculate with it, I would tell you to turn it to kilograms, but it doesn't matter in this case because that's the number we're after, and he gives the mass of the card in grams. So I would say either, whichever you want. Cool.
So I got, for the third one, I got force was 0.429 and the acceleration was 0.518, I think. Let's make sure. Yeah. Force was 0.429, and then the acceleration is 0.518. Yeah. Which came out, the slope was 0.83 or 0.828. Yeah, I get, yeah. He wrote something right now? Oh, no, I missed it. It goes quick.
I wonder if you could just like keep it up there. For the 4, right? Yeah, 0.4. The force, yeah, 0.4. Yeah. 4. I think it's 459. Hold on. What did you say you got? Oh, yeah. That's what I got. Yeah. Is everybody else getting it?
Yeah, got it.
So are we converting the slope too to grams? Okay. Find mass on the next one and divide by 3. Wait, your slope is, how did you get the 459 for the 4th one? What did I do something wrong? The force is 0.433, and then the acceleration is 4.459, right? So then the slope should be 0.943.
That's what I have.
Say again? Oh, that one that was 0.943. Wait, and then you got the masses 0.943 because you were just.
Well, those were the slopes, right?
This meeting is being recorded.
No. Oh, I don't know. I thought like mass of each hex was the extra mass plus the mass of the empty cart.
The not quite. Oh, good. Here we can do this really. As people come in, hang on. Let me I'll share this. So the idea is you found the slope. The slope is the total weight, total mass of cart plus hexes, right? That's what the slope is. And so that was your average force divided by your average acceleration, okay? Once you have the slope, you subtract off the mass of the cart. So the mass of the load, I called that extra mass, equals the mass of so extra mass equals total mass minus the mass of the empty cart. So Joyce, it sounded like what you were saying was you had like a 425, for example. I don't remember exactly what it was, or like 495, and then 550 something or other. So it sounds like these are getting bigger, and the reason they're getting bigger is because that's the total mass. So the slope that you read is the total mass. What you want to do is subtract the mass of the empty cart, which is always 392. That will, and whatever is left over, that's the mass of the hex bars. And if you only have one hex bar, whatever's left over is the mass of the hex bar. But if you have 3 hex bars, then whatever's left over is 3 times the mass of 1 hex bar. So I was glancing at it. I haven't done it myself, but I think they're somewhere between like 75 and 100 or something like that. Did anybody get a value?
For the mass of each individual hex?
Mm-hmm. Yeah. Well, I'll let you calculate it. It shouldn't be too bad. I also modified the table to give a little bit more instruction so that it's inside the table what operations to take to form the values in that table. And look, each time you find the mass of the hex weight, it may be a slightly different number, right? And that's okay because it's an experiment. But as far as I know, as far as I could tell, the hex weights are identical. And so that's why I said at the end, take an average. So maybe for the first data set, you get a mass of 75. And for the second one, you get a mass of 83. And for the third one, you get a mass of 67. That's all fine. Take the average, and then that'll be our best guess of how much those things weigh. Alrighty.
I had a question about the total mass. How do you find the total mass?
Right. So the total mass, that is, remember, so what you're looking at is you've got a plot of acceleration versus time, right? And you've got a plot of force versus time, right? And so what we're looking at is the slope of F versus A. So that's like F divided by A. That's the slope, right? And so if you look at those diagrams, there's those boxes, and here it'll say the mean A, and down here it'll say somewhere in the box the mean F, right? So you'll take this number, divide it by this number, okay? And then that tells you the slope. The slope is the mass. Remember, F equals ma, right? So this is a linear relationship, right? And the slope is whatever number is in front of a. So the slope of this, the slope is the mass. But that's the total mass. It's everything you're pushing. It's everything you're pushing. And that's why when you add weight, the slope keeps going up because the total mass is increasing.
Oh wait, could you also go over how to find the mass of each hex? Because I only understood up to how to find the extra mass.
Okay, cool. So you've got the total mass, okay? And then you find the extra mass by taking the total mass and subtracting the mass of the empty cart, which is always 392. So that's your extra, right? That's the mass of the load, okay? Well, all of that load is hex bars. So I'll just give you some numbers. Let's say that for trial 1, I'm not saying this is what you'll get, but for trial 1, there was 1 hex bar on it. For trial 2, there were 3 hex bars. Remember, we're ignoring the one where there were 2 hex bars. And then for the third table, there were 4 hex bars. Well, you may find that your calculation for mass extra for this one is 75. You may find that your calculation for M extra for this one is like, I don't know, 200. And you may find for this one that it looks like 250. So these are your M extras. And this extra mass is due to 4 hex bars. So the mass of each hex bar, mass of each hex, right? That is 75 divided by 1, the extra mass divided by the number of hex bars, or 200 divided by 3, or 250 divided by 4. I'll get some number here, some number here, and some number here. They're not guaranteed to be the same number, but they'll be close, hopefully. And you'll take the average, whatever the average of those numbers is. That will be your best guess for the mass of a hex bar. Does that help?
Yeah, thank you so much.
Sure, you got it.
Also, each hex bar is the same like mass?
I think so. I don't know so because they don't say in the video, but they sure look alike to me. So I am assuming that they're all the same mass. But Max, that's a very good point. It may be that they are randomized hex masses, but I don't think they are. I don't think.
Thank you.
You're welcome.
Hi, Professor. I'm sorry, but for number 11, like, are you just supposed to search up the conversion on Google and then do dimensional analysis? Or I'm not really sure.
Well, let's take a look really quickly. We'll look together. I don't remember what 11 asks. Let's see. Oh, based on your results, what does 1 Newton appear to be in terms of kilograms, meters, and seconds? Well, hang on just a second. No, you don't need to Google it. So force over acceleration, right? That's the slope. We just said that's the slope. And we also said that the slope is mass. So somehow the units of this have to equal kilograms. Sometimes when you do unit calculations, they draw little brackets around the things just to say that it's not the actual value of it, but the units we're interested in. And so if you look here, the units of F divided by the units of A. What are the units of acceleration? Does anyone know?
Meters per second squared.
Awesome. So meters per second squared, somehow this has to equal kilograms. So that means that the units of F, if I multiply both sides by this, equals kilograms times meters per second squared. So this is a derivation. I'll put derivation of the units of force. And so this whole time when we've been saying newtons, right? This is also newtons, right? We know that 1 Newton is 1 kilogram meter per second squared. Does that make sense?
Yeah, thank you.
Cool. Yeah, it's funny. We live in a world where I'm not teasing you. I like the way you asked. You're like, can I just Google it? And you know what? Like almost every single question in this module, you can Google 100%. Everything that comes out of my mouth, you can Google, but it's better if you don't. It's better if you calculate it, right? Because then you'll have that skill, right? And I don't know if you remember, we talked about the Karate Kid. You know, if you don't practice your karate, you get beat up. So if you spend a lot of time Googling answers, when the exam comes and you can't Google anymore, you're going to be in trouble. All right. Also, man, I know I talk so much. I'm sorry, I can't help it. But this just reminded me really quickly. Like sometimes if you're not, like if you're into this stuff, you're like, yeah, this is great. If you're not into this stuff, you're like, why? Why are we doing this? What is the point of this? These are like mental gymnastics. These are just stupid tricks. I'm just using equations and going in circles. Like, what is the point of any of this, right? And hopefully, the more you use the equations, the less it feels random. Like when we set up our force problems, this is really a method of looking at the world where we're trying to be systematic, right? And we're learning how things work in this super systematic way. And you may say, well, I don't care. Who cares about this? I want to go and I want to make great art, and that's awesome. You should want to go and make great art. My sister's boyfriend is an artist, and he basically said we have family Zoom every week, and he basically said to me, he's like, what's the point of all that? And I said to him, what's the point of art? And he's like, well, art is beautiful. And I said, so is science. And he scoffed at me. He's like, that's ridiculous. I said, well, look, when you look at a sunset, you're an artist. You see all kinds of stuff that I probably don't, because I am not an artist. You see the exact colors that are there, and you understand the beauty of it because you're like, oh, that shade of this, how they work it in, that is amazing. I don't see that. To me, the sunset's beautiful, right? But I don't see as much as he sees, right? By the same token, when he looks at the world, he does not see the same thing that I see. I don't just learn about science so that I can build contraptions, although it's useful for that. I learned about science because I'm telling you, honestly, the world looks more beautiful when you can see how it works. It doesn't make it less beautiful. There's a poem by Walt Whitman called When I Heard the Learned Astronomer, and you can look that up. And Walt Whitman basically makes the case in that poem that science ruins everything. You know, like he talks about going to this symposium, and these astronomers are going on with facts and figures and numbers and tables, and he feels like he has a headache. And then he steps outside for a breath of fresh air, and he looks up at the stars in the night sky, and their beauty and meaning is clearer than ever. But that is not true, because all those astronomers who are in that meeting can also look up at those same stars and appreciate exactly how beautiful they are, the same way that the guy who doesn't know about those facts and figures do. But the astronomers appreciate it even more. They appreciate how amazing it is that the sun, that each one of those stars is a sun exactly like our own, and that the only reason they shine is because of this crazy delicate ballet balance between all of these moving particles inside of it, which don't even want to be close together, but are smushed together by exterior forces and shine. All this beauty that you see, understanding it doesn't make it less beautiful. It makes it more beautiful. Okay, all right. I'm going to stop. That's my defense of physics for the night. I know no one challenged the beauty of science, and I don't even know how I got on that topic, but I encourage you to think of it in those terms, not what can I do with this, but why does this make the world look more beautiful? Because that's the reason. The point of science is because it's beautiful. And I don't mean that in a geeky way, like it's fun to calculate. I mean, literally, you will find beauty in things that you never did before. You see a rainbow reflecting off of an oil slicked puddle, and you will see the same rainbow that someone that doesn't understand how it works. But you'll find it. I promise you'll find it more beautiful. Okay, enough of that. By the way, I found out why this calculation for our moon gravity didn't work. The number in the module is wrong. This is not the mass of the moon. It's the mass of a moon, perhaps, but not our moon. This is the mass of the moon, which I looked up. And if you use this number for the mass of the moon, you will get the correct acceleration, which is 1.67 meters per second squared. Okay, let's do some problems together. We'll do a couple of really quick ones. We'll just bang them out. So they'll all be 1D problems because your homework's only 1D problems. And then 2D, even though we looked at it a little bit last week, that was kind of to give you an idea of where we're headed. We'll do a bunch of that on Wednesday. Okay, so the first thing is a robotic arm without a payload accelerates horizontally from 0.1 meters per second to 1.5 meters per second. So they give a V initial is 0.1, V final is 1.5. I'm leaving off units because I'm lazy and I want to go fast, but technically they should all have units. And they say the displacement is 1.8 meters, okay? They say the robotic arm has a mass of 20 kg. And they want to know what's the force. And notice they say net force, because of course, if I have a box, I can push on it this way, but if I'm also pulling on it this way, all that matters is how these things add up. That will tell me the acceleration. Each individual force doesn't tell me anything. I need to use this fancy sum thing, and that will tell me mass times acceleration. Okay, so in this case, let's see. The acceleration, I have V final squared equals V initial squared plus 2a delta x. This is from my kinematics. It's just one of the formulas I picked, right? So V final is 1.5 squared equals 0.1 squared plus 2 times a, which is unknown, times 1.5. This is 2.24 divided by 3 with yeah, that equals a. So that's some number. Once you have the acceleration, then you can say, okay, force is mass times acceleration. So 20 times 2.24 over 3. Okay, so that's this. So that's a good example. So if you ever see, forces have to do with acceleration. If you ever see a problem and they don't list an acceleration, your job is to see how there's an acceleration hiding in the problem. All righty. This one's fun. I saw this and I wanted to talk about it. So a 65 kilogram man is trying to run across an icy pond. The coefficient of friction between his shoes and the ice is 0.16. What is his maximum acceleration? You'll see this word like, what's the minimum of this? What's the maximum of this? And it can be hard to interpret what that means. Also, like, you probably don't think that walking requires friction, but in order to push yourself off the ground, you can exert, a downward force and the normal force will push you up. But in order to move yourself backwards and forwards, you need a force that is parallel to the ground. And the only force is friction. So every time you take a step forward, when you are pushing your foot back, you're taking advantage of static friction. But if you're on ice, your feet are not still when they hit the ground, they slip, but there's still friction. And you can take advantage of that friction to keep propelling yourself forward. So in this case, I'll just make a little free body diagram. There's some force that's being exerted this way. That's to move forward. There's another force of, oh gosh, I'm sorry. So two separate objects. So this is another reason I wanted to talk about this. Here's you. Your feet push backward on the ground, right? So the earth or the ice feels a force backward. But by Newton's third law, right, that means that the force on you points forward. And there's only one agent available for that force, and that's the friction force. So I make this a funny F. I put a K on it because we acknowledge that the feet are sliding, okay? And then they say the coefficient of friction is 0.16. So I would say force of friction equals mass times acceleration. I'm sorry, I'm getting ahead of myself. The force of friction we learned is mu sub k times the normal. Okay, that equals mass times acceleration. So mu sub k, the normal, so if we just think about this, that's how hard the ground pushes on the person, right? Well, their weight pulls them down, mg down, and the normal will cancel it because they're not jumping up or sinking through the ice. So those cancel because they're not accelerating. That means that the normal force is equal to the weight. Mg equals ma. Let's get rid of these m's. And we can say that the acceleration caused by friction, which is the maximum acceleration, is mu k times g 0.16 times 9.8, whatever number that is. Sorry, acceleration is. Oh yeah, I'm sorry. I don't know why I got rid of it. Mu kg, that does equal that. That's the acceleration. Okay. A parachutist, so falling from the sky. I always forget. Sometimes I think this class ends at 10. Sometimes I think it ends at 10:10. It's 10:10, isn't it? No comment.
I'm
I
not
think
sure.
it's 10.
Is it 10? Okay, I'll stop. I won't. I won't. I don't want to keep. I don't want to keep people late. I will. I'll put together a little video, and I'll post the video under nutshell videos where I attack a few more of those, and you can check them out. You will have the homework, and that'll be your opportunity to practice. But for all these problems, I encourage you to make a free body diagram. Whether you think you need one or not, make a free body diagram anyway, and then. Try and translate that into F equals ma and then solve for the acceleration. Okay, does anyone have questions?
No, I don't think so.
Okay, cool. And I have office hours tomorrow, Tuesday, 9 o'clock. Everyone is welcome.
Thank you.
You're welcome.
All right, see you Wednesday.
See you Wednesday.
Thank you, Professor.
You're welcome. You're welcome. Bye. All right, hang on. I see your question.
Okay. So I think what we want to do here, we're gonna do everything, replace the terminal, this stuff. Oh my god, we'll have this to no longer show on the long over here, and then down to the bottom. It's got an interface on the bottom of our furnace. We'll have this cable running along over here, and then down to